Welcome to breadboarding. In the previous video we managed to get our 386 breadboard adapter all wired up and tested, and we installed it in our test breadboard here, and we've got with it a power supervisor reset circuit, a 16 MHz oscillator and some additional clock circuitry to drive the CPU. We've also got dip switches to allow us to set all the data values for all 32 data bits. I've also connected a 32-channel logic analyzer which is connected to all the address signals of interest and a couple of the control lines as well. So this is video number 5 of the 386 Breadboard PC series, and in this video we're going to be testing the 386 CPU with our no operation code instructions. And in fact it turns out that there's a problem actually with using this. We end up generating something called a general protection fault, so we'll be going into the background of this and finding better ways of testing the CPU. Now it's probably worthwhile just also to have a quick look at what no operation code actually is. And there was some feedback from the earlier series of videos. So this is the IBM PCXT technical reference guide, and this shows that the no operation code is actually 1001, so that's 9, and this is N0. Now in actual fact, in the original Intel 8088 and 8086 datasheet, there wasn't a no operation code, and I'll explain the reason why. And this is now taken from the 386 datasheet, and we can see we have a no operation code now in the Intel documentation, and it's 90. But if we also look at the exchange instruction, so this is to exchange registers with the accumulator, so the accumulator is normally known as AX. If we look at the register exchange with accumulator, then in fact we can see here that it begins with 9, then it has a 0, and then it has 3 digits to determine the register. And if we then go and have a look at the register, we can then actually see that when we have 000, that's in fact AX. So in actual fact, the no operation code is actually exchange AX with AX. So it obviously doesn't achieve anything, and so that is in actual fact the instruction which is actually being executed when we put no operation in an assembler. Then in fact what it's using is exchange AX with AX. Now when we look at the logic analyzers, there's a couple of the signals, so the memory I/O signal, the data control and the write or read signal. These 3 control signals are actually decoded in the datasheet here. So this is a bus cycle definition. So you can see that the values from 0 to 7 are defined here. So things like interrupt acknowledge, reading memory code. So this is reading code from memory versus reading data from memory. So when we have a look at the logic analyzer, this is where some of these numbers have come from. So now let's look at the logic analyzer. So this is the 32-channel logic analyzer. You can see most of the channels are enabled there. We've basically got all the address lines, so processor address, starting in fact from 2 all the way up to 23, and then we've got a gap when we then get to 31. Now the reason why the order of these is a little bit different is because in order to analyze this in the most practical way, you can see here that because we don't have the address lines 0 and 1 because we've got 32-bit data, and so in fact the A0 and A1 lines, there aren't actually those address lines. We actually have the byte enable 0, 1, 2 and 3 determines whether or not we're reading the 0, 1, 2 or 3 bytes. So effectively replaces A0 to A1. And we've also got everything going up to address line 15. Then when we look at the higher address lines, you can see that we've got 16 up to 23, but then we've got a gap until we get to PA31. And because these other ones are not actually in use, I was finding with the logic analyzer I need to have one of the signals set to 0 volts, and this just means that the numbers are actually coming out a bit cleaner. And you'll also see down the bottom here we've got some control signals. So we've got the reset line, the address strobes. When this goes low, the CPU is telling everything else that there's a valid address on the bus. Then we've got the write, read, data control and the memory I/O, and then finally down the bottom here we've got our clock 2, which is the 16 MHz clock going into the processor. So this is going to be triggered on reset going low. So when it starts up, reset will be set to high. So that will keep the processor in reset state until about sort of 250 milliseconds after the power's come on. That just allows the power to stabilize. And what we'd expect is to see that the no operation codes would be read from the data bus, and that basically you would cycle through all the addresses. And in the 8088, in fact, what you'd see is when it got to the end of the 1 megabyte address space, so it got to FFFF, then it would actually go all the way back to 0, start from 0 and count all the way up again until it overflowed again. So that's what the 8088 does, and we're going to expect that to happen with the 386. Okay, so let's turn it on, and you'll see that the lights down here, that the red light will come on initially to show that its processor's in reset, and the green line will then show when the processor is running. And we've also got our 90909090 all set on here. So I'm just going to set the logic analyzer to be waiting for the power to come on. Turn the power on, just move the cable so you can see the lights. So you see that the red light came on initially, that's when we're doing the power on reset, and then green means the processor was running. So let's take a look now at the logic analyzer output and see whether or not we've got some life coming from our 386 processor. So here we have our logic analyzer, and we can see that in fact when we first turn the power on all the way back here, see that because reset was 0, it's actually triggered it. And we can see that in fact that after this period of time, so if we look, we had some timing markers, so when the power goes on, when it comes out of reset, that was about 313 milliseconds. So it's between about 250 and 400 milliseconds normally, the power on reset. So during this period of time, the reset signal is held high. So on the Intel CPUs, then reset is active high. So we can see there's not really very much going on. And on the address bus, we can see that in fact the lower address has got FFFC. And the reason why we have that is because the A0 and A1 aren't enabled here, they're 0. And so that would have made it up to F if those were there. And in fact, the top address lines, the A16 up to A23 are all 1s. But because we've only got the A31 and the other ones are all 0 that I showed you earlier, then in fact this would effectively be FFF. If we actually had all of the address lines connected up to here, we would actually see 4 Fs there. So that looks like the initial address is all 1s when it all starts up. And then we can see here that when reset finishes, then we should then see some activity. So if I just put some more timing markers here. So when reset finishes, and the first activity, when you see the address strobe here, address strobe indicates there's a valid address on the address bus. So that's really the first time that we get anything valid here. So if we just look in and have a look at what that period of time is, we can see here that this is about 25 microseconds. So from the reset signal going low to the first instruction really being executed is about 25, 26 microseconds. So it takes a little while. In the original 8088, I think it was about 6 or 7 clock cycles that it took. And we'll have a look and see how long the 386 requires here. So we've got our first couple of instructions here. So let's see what's happened here. So it's actually reading FFF0. So this is the reset vector. So this is where the Intel processors look at the very top of memory. And because we know that the top address bits here are also going to all set to 1s. So just because we've only got the address 31 and then 16 to 23. So this is effectively FFFF. So it looks like we're reading 4 bytes from F0, then another 4 bytes from F4, another 4 bytes from F8, and then something happens. So it looks like it's starting, but then something has sort of happened, which we can't really explain. If we look down here, this is the status information here. So at this point in here, you see if we go back to the other slide, we can see that 0 is interrupt acknowledged, for example, and reading code is 4 and reading data is 6. So after a period of time when the reset ends, we do actually have a code 0, which is interrupt acknowledge, and then 04 is actually reading code. So at this point in time, it's reading code, but then there's a bit of a gap. And when we see our next address strobe here, you can actually see that, in fact, we're not actually executing the next instruction. We're actually reading from 000, so this is in the bottom sort of 64K of RAM, and we're actually reading from 34 hexadecimal. Now, I happen to know that this is where the Intel processor has all its interrupt vectors. So in fact, this sort of set me off looking at something, and I'm just going to switch back to some slides where I've taken some screenshots from here and I've annotated them just to help to explain what's actually going on. So what I was expecting is that if it was like the Intel 8088, then we should have got to FF at the end, and then it had gone to 0, and then going 0, 1, 2, 3, 4, 5, and going all the way up through the address range. And that's not actually what we see. If we actually look at the next instruction here, we can see that the lower address is 9990 and the upper address is just 9. So that doesn't look quite what we're expecting. And so I'm going to try and explain what's going on there. So in fact, what's happened here is it's about sort of 25, 26 microseconds after reset ends. And we know that the upper address lines are set to 80FF. And the reason for that was, as I showed you, is that the lower 8 bits from PA16 to PA23 are all 1, so they're FF. But because we only have the address PA31 here and all the others are effectively set to 0, then that's why this is 80. If all these other ones here at 0 volts were set to 1, this would also come out as FF as well. So what's happened is it's read 4 bytes of no op, then another 4 bytes of no op, another 4 bytes of no op, and then it's tried to read the next 4 bytes, and in fact something has happened. And what in fact has happened is it attempts to read beyond the end of the current segment. The code segment, when the CPU resets, is actually set at the very top of the 32-bit of memory, so at the top of 4 gigabytes of memory. And in fact, when we're actually trying to read the next one here, the memory address after that is actually going to go over the end of the segment. And in fact, what the actual problem we've got here is something called a general protection fault. So this is our 3.4 read. Now, this is in the interrupt vector table space. And in fact, if we look into this, this is about another 9 to 10 microseconds after the read beyond segment. And this is the next valid address that we can see here with the address strobe here. Now, it happens to be that 3.4 is an interrupt vector. Now, generally, interrupt vectors have 4 bytes. So to actually know what interrupt number this is, we need to divide the 3.4 hex by 4, and that happens to give us 0D or 13. And what this actually is, when we actually look it up, it's an attempt to read beyond the segment. So the code segment had actually gone beyond FF, when it's trying to go back round to 0. And in fact, it's a general protection fault and a segment overrun protection. Now, if you go into the 386 documentation, this is all the interrupt numbers. And in fact, 13 here is general protection fault. And then there's another table later on, and it actually says in the table that when we get segment overrun exception on the code segment, in fact, is what we were using because we were just reading code at the time. And that means that when we try and read beyond FF, then we'll actually get this exception. So what the processor is actually going to do is when this general protection fault occurs, and those of you who are old enough may remember in Windows 3.1 that general protection fault was a sort of the old school equivalent of the blue screen of death, which we'll come to in a few minutes. What this indicates really is that although the processor is emulating the original 8088, it's not actually doing exactly the same thing as what the 8088 does. So in fact, we can't use the no operation code in the current form to be able to provide a nice test of the processor. But in fact, what it will now do, it'll actually load the segment address of off the data bus, which will be 9090, and it'll also read the program counter address off of the data bus, which again will be 9090. So because we're setting the data bus always to be 9090, then in fact the address that this is going to pick up to run this particular interrupt is going to be 90909090. Now when we then have a look at where this ends up, you can see here that our next address strobe here for providing a valid address is in fact not 9090, it's actually 9990 and 9. And if I just show you how that comes about, so effectively we've read the 9090 and 9090 as our interrupt vector, but in fact it starts executing from this segment 9 and 9990. In fact, if you work this out, because segments generally are multiplied by 16 or rotated left 4 bits, so effectively the segment here is 90900, and then we have the right hand side of things. When we add those together, we actually get 9990, and then the upper segment is 9. So in fact, what's happened here is we've gone beyond the end of the memory. The 386 processor has trapped that as a general protection fault, and in fact it's then read the interrupt vector from the data bus, and because we've hard-coded the data bus to be our no operation code, it's actually started at 990 here. So it took me quite a while to work the way through this. It's stuff that I've not come across before, having not really worked at this level of detail with 386s. So I'm just going to now show back in the logic analyzer to see what actually happens after 9990. Okay, so we got our 9990 there, and if we actually zoom out a bit, we'll see that in fact the addresses do go up. We've got 9B78, 7C, so it is actually going up. It's not particularly easy to see, but if we actually have a look at the high level, we can actually see that our address lines are sort of going in this sort of pattern. So this sort of pattern is what we'd expect when we've got binary data sort of going up in sequence, as it were. Every now and then we'll find that there'll be another gap here. And so I think what we'll find, if we drill in here, we look at the last bit here, we can see that we've got 08FB, I think, there. In fact, if we look at the next bit here, look, we've got a general protection fault interrupt again occurring. So what appears to be happening is that it will start counting up for a while, and if we go through all these, you can see that these are actually counting up through various sequences and things, but then we're getting another general protection fault again. So we're not getting quite the clean sort of progression going from 0 all the way up to lots of Fs that we'd expect. And in fact, that we're getting this general protection fault occurring on a sort of regular basis, which is effectively restarting things back at our 9090 based address. Just to summarise that, we can see here that we basically get our addresses are progressing, and part of the reason for doing this no operation test is just to make sure that all of the address lines are effectively connected up properly, and we can see that there's some sort of progression going on here. So we are getting some sort of ascending address progression until we get our next general protection fault. So on here, this is the gory detail about what is actually going on here. So this comes from the 386 datasheet, and what it says is after reset, it will start executing. So this is 16 bytes below 4 gigabytes, the top of 4 gigabytes. And when the first intersegment jump or call is executed, so this is a far jump. So this is a jump that includes both the segment and the lower address or offset, as it's known. And what the processor will do is to set all of the A20 to A31 will drop to low values, and the Intel 386DX will only execute instructions in the low 1 megabyte of physical memory. So basically, when we do the first far jump, 386 will behave like the original 8088. But at the point in time where we're doing our no operation codes, we haven't done a far jump, so I don't believe it's actually switched the processor into this sort of lower 1 megabyte mode. So this is the reason why our no operation perhaps not having the desired effect that it did on the 8088. And the other thing down here, it says after reset has gone low, between 350 and 450 clock 2 periods after reset becomes inactive, it will start executing instructions. So when we were looking at the logic analyzer there, we could see that there was actually about 25, 26 microseconds. So in fact, if we work this out with the 16 megahertz clock that we're feeding into the processor, 350 periods is about 22 microseconds, 450 is about 28. So that's about in the middle there. So that's the sort of gap that we'd expect from the processor finishing reset and reading the first instruction. And then over here, this is actually the bit that gives us the information about why we're getting this general protection fault. So after a reset, then the code segment is set at F000, but it says down here with note 3 that a limit is set to FFFF. Now that limit is part of the 386 protection mechanisms to make sure that if programs actually go beyond the end of the segment, then it isn't actually going to cause problems. Now, on the original 8088, there's certain programs and things made use of that. And so in actual fact, in the design we're going to be doing, we're going to be disabling the A20 line under some circumstances to ensure that compatibility. But in its basic mode that we're booting things up in at the moment, it's actually protecting ourselves from going back to 0 in memory. So what we need to do is to find a way of actually working around this. So I don't think we're going to be able to use just the pure no-ops to test the processor in quite this way, although it does show that it is working. So if we go to the hardware reference, in section 11, there's actually a simple diagnostic program. Now, it doesn't say, oh, you can't use no-ops, and it doesn't explain any of this stuff. But in fact, this does actually provide a very simple program. It actually has 2 no operation codes, and then it has a jump that basically just goes back a couple of bytes back to the beginning there. Now, the reason why I have upgraded the test board here to have 4 bytes worth of data is so I can actually try this. So what I'm going to do now is to set these bytes actually on the data bus, and I'm going to reset the processor again and see whether or not it just goes round in circles. This should mean it will just go from the very top of memory at FFF0, go all the way up to here, and then bang it around again. So we should be able to see that just go in an infinite loop. So I'm just going to go and set the switch values on that, and then we'll come back and see what happens there. So I've set the bytes on here. So the least significant bytes, we've got 9090 EBFC. So this is the jump, and this is the offset that gets it to go a couple of bytes backwards. So I'm just going to run up the logic analyzer and turn the power on. You'll see the green lights running shows that the CPU is running. And if we go back and have a look at the logic analyzer, so you can see we've got some activity here. There's a bit of activity on the lower address lines, but not very much else elsewhere. And we can also see, if we look over here with the decoded results, we're only showing PA16 to PA31, so that's 80FF. So it's remaining actually in the high area of memory at the top 4 gigabytes of RAM. And if we just scroll down so we can see some of the other data, we can see that just as it comes out of reset, we had the status there of 0, which was interrupt acknowledge, and then we've actually got 04. And in fact, the status here of 04, which is read instruction, if we look at the control lines, the write read, the data control, and the memory I/O, you can see these haven't changed at all. So basically the rest of the data here is always going to be reading code. And then if we look up here, we can see that where we've got the address strobes, we've got 3 lots of addresses, the FFF0, FFF4, then FFF8, and then it goes back to FFF0, F4, F8. And we got almost a second's worth of data here. So if we go to the very end, and you'll see that we've still got the same cycle. So it looks like this is actually now going around a continuous loop. We haven't got any exceptions occurring. And so this sort of shows that the test that Intel included in here is a valid test. It just doesn't show very much interesting information on the address lines. So if you just have a look at the bytes that we put in here. So this is the 4-byte test code that Intel provided in the developer guide. And what we actually did is we had the lower 8 bits were 90, no operation. The next 8 bits were 90, then we had the EB, which was the jump, and then we had FC, which was the offset that basically says go back to the start there. So that looks like that was working. So it looks like we've got our CPU is working, and with this sort of Intel provided test, then it looks like we've verified that the lower address lines are working, but we haven't really been able to test the higher address lines. So as I mentioned earlier, those of you may be familiar with Windows 3.1, then general protection fault was the old school equivalent of the blue screen of death that we would have in more recent versions of Windows. In fact, in Windows 3.0, there were the dreaded things called unrecoverable application errors that used to cause a lot of applications to crash unexpectedly. And Microsoft announced in Windows 3.1 that unrecoverable application errors would no longer occur, and that's partly because they were just replaced with general protection faults, or GPF. The general protection fault is generally caused by 386 and higher processors when there's some sort of memory problem. So I'm proud to say that I've managed to generate general protection faults of just 16 no operation codes. And the Wikipedia article on this, which the link will be in the description below, will go into a bit more detail about this. So this is the 386 version of the high-level plan that I've used on the previous Breadboard PC projects. Really split into 3 phases. The basic NanoComp 386, which is to get a simple computer together with the ROM or EPROM, memory, an LED display and keypad, running the NanoComp 86 monitor with the serial port and the ability to save and load files over the serial port. And this allows to get a certain amount of debugging information done before we actually manage to get the floppy disk PC running MS-DOS, and before we add hard disk and try and get Windows 3, 3.1 and even Windows 95 running. And should we be successful with that, I'm also going to try and get an early version of Linux running as well. So we've managed to test our 386, at least it's sort of responding to the clocks and reset, and we're able to show that a very, very simple program from these dip switches is actually running. In the next video, I'm going to be looking at seeing if we can make something slightly more interesting in these 4 bytes that we've got for writing a program, probably one of the world's smallest programs. So I'm going to be experimenting with a couple of options to see if we can get a bit more activity off the address lines using some 4-byte programs. I'm also going to be looking into using the processor internal testing, which if we set the busy line low during reset, then theoretically the chip will go into reset mode. So we are looking more at testing the chip in the next video. So if you don't want to miss out on future videos, please hit subscribe. And when you hit subscribe, if you choose the option with the bell and all, then you will get notifications when new videos get published. I'm generally going to be trying to publish 1 to 2 a week over the next month or 2. Please feel free to leave comments. I do try and respond to comments within about 24 hours or so where I'm able to. And if you found the content interesting and useful, please hit like. It just helps to make the videos available to more people on YouTube. Thanks for watching.